who's just joined us in the Zoom chat. We're just getting our stream set up for YouTube. There we go. Oh, all right. And I'll ask everyone to make sure that your video is off, please. Excellent. All right. Welcome to the Friends of the DAO Saturday Night Star Party. I'm Aaron. I'm going to be emceeing this evening. We'll give it another probably 1 or 2 minutes just to let anyone else join us and then get started. If you're in the chat while we're waiting for folks, we'd love to hear where you're visiting us from. I know many of us are local to Victoria, but if you're from further afield, we'd love to hear where you're watching from. Throw that either into the Zoom or the YouTube chat. Got some Brentwood Bay. I'm currently in Brentwood Bay right now. Despite the background, I'm actually sitting at home. Wasn't able to make it up to the center this evening. Hopefully I'll be up there next time though. And that is my cat. All right, so I think we've got just about everyone joined us now. So I'd like to start us off by acknowledging with respect the Coast Salish and Lekwungen speaking peoples upon whose traditional territory the observatory stands, and the Songhees, Esquimalt, and Masonic peoples, nations whose historical relationships with the land and the sky we all share continue to this day. Tabitha says hi. I'd also like to say, if you join the Friends of the DAO as a member or renew your membership in March or April this year, we'll be sending out a free gift with your membership as well from our gift shop. And if you're watching on YouTube today, please like and subscribe. Even if you're in the Zoom chat, if you want to, or in the Zoom call, if you want to visit us over on YouTube as well, throw us a like. That really helps us out and helps us extend our live stream to more people around the world. You can also follow us at our social media, so Twitter, Instagram, Facebook, YouTube, and YouTube. For Twitter, Instagram, and Facebook, we are at Friends DAO, all lowercase. And you can find us on YouTube by searching Friends of the DAO as well. We'd also like to hear from you how you heard about us this evening. We'll be throwing a poll into the chat on YouTube and in Zoom. If you want to give that a click and let us know how you heard about this event. And let's see what we got next. Yeah, so I think we'll get started with our programming tonight with Dawn Moffat. She's going to tell us a bit about what's up in the sky this evening.
Okay. Hi, everybody. And I guess you've all noticed that Aaron actually has the Cheshire cat because it disappeared into his background while he was talking, which is a pretty neat trick, I think. So
I think you can still see her smile, though.
Yeah, at times. So yeah, welcome everybody. And I'm going to tell you a little bit about what's happening in the nighttime sky over the next month, what you can see mostly with your eyes. And this weekend is the full moon. And for professional astronomers, and for amateur astronomers, it's usually the weekend off because you really can't see a whole lot because it puts out so much light. And for new telescope users, you might have noticed that it's really hard to see craters and other features on the moon around this time, because what's happening is the light from the sun it's high noon on the moon at this time, but light's coming straight down onto the surface and there's very few shadows. And I bring this up because a friend of mine actually mentioned the difficulty in seeing craters a couple nights ago around this time. So there's a couple of reasons why it gets so bright around this time too. And one of the reasons is because the moon isn't a perfectly smooth ball. It's actually very, very craggy relative to its size. And so there's a lot of shadows. And so there simply isn't sunlight hitting a lot of the surface in the earlier phases. And so it's a bit darker than you would expect for the early phases. And as we get towards full moon, it becomes more illuminated. But strangely, the moon doubles in brightness in the couple of days around full moon. And that was actually a bit of a mystery until the Apollo astronauts went to the moon. And it turns out that the surface grains actually reflects sunlight really, really well back along in the direction that the light comes from. And so at full moon, the light is bouncing back towards the sun, and we're pretty close to that line. And so the moon nearly doubles in brightness. So you would expect that that the full moon, just based on the phase, would, because it's a big circle, would be twice the brightness of what appears to be the half moon, what we call the first quarter moon, but it's actually about 10 or 11 times as bright around this time. So it's super bright. And in fact, the ground is illuminated by the moon about 250 times more than starlight is. So it's you might want to take a look at that over the next few full moons and see if you can see that effect. And so you probably noticed on the internet, there's all kinds of names for these different full moons with various cultures, which is kind of interesting, but they're all full blast moons. So full moons are always full blast moons. So maybe if it clears up tonight or maybe tomorrow night, to see if you can go out and see how bright the moon is. But let's move over. There's the moon as we would see it after it gets dark tonight. But let's move over and have a look at sort of the southwestern part of the sky, and we can see that the winter constellations are still visible. They're still hanging on. And if you look up at Orion, you can see that in the springtime, Orion's belt is pretty much horizontal, and Betelgeuse is right above the belt. So Betelgeuse is the star that had that mysterious dimming last year, but it's back to full brightness now. And if you look over to the right, you can see the star Aldebaran, which is quite red, but Mars is directly above it. So if you're getting confused about which is which, Mars is above Aldebaran. And later on, next month, there's actually going to be a couple of close approaches between the moon and the planets. And so if I can just sort of move this ahead to, let me just move it to April 16th. We should see the moon quite close to Mars. So if you're still having trouble identifying it, you'll notice that the moon is close to it on that date. And if you're in middle of Africa or India, the moon will actually come very close to Mars. In fact, will actually completely cover it. And on the earlier in this month, let me just flip the date back again to around the 6th. And I'm using Stellarium, by the way. Oops. Not using it very well at the moment, as you can see, but let me just try that again. So if we just move the time ahead here to the morning sky, and I'm just going to flip it to, actually, I'm going to flip it to about 6 a.m. And we'll just make it a little bit earlier. And we'll look towards the southeast. And if I'm doing this right, you should see that the moon is down close to the horizon and it's just a little bit below Saturn. And so Jupiter and Saturn are coming back into the morning sky over the next little while. So there's a couple of things to look for over this month. And there will be a meteor shower this month, but there will be a full moon that's, or nearly full moon rather, that's interfering in the way that we just described. So lots to look for in the nighttime sky over the coming month. And the sun will, the sun's currently setting around 7:30 and will set around 8:30 by the end of April. So of course, full darkness doesn't really happen for an hour and a half past that. Okay, thank you.
All right, thanks very much, Don. Next up, we have Ben Dorman. It's a bit about some new results from the Event Horizon Telescope in the Atacama Large Millimeter Array at the center of another galaxy. Let's see, do we have Ben? Ben? There we go. I think you're still muted, Ben.
So I thought I'd give you a brief guide to black holes this evening. You see on the top two pictures here, there's a couple of different kinds, and I thought I would go into the differences, but mainly we're going to talk about the guy on the right. First of all, about understanding black holes. It was 1798 when Pierre-Simon Laplace posited the idea that if something was massive enough, light couldn't escape from it. So the idea has been around for a couple hundred years. Then Einstein in 1916, with his theory of general relativity, posited that massive objects curve space. And he came up with a set of equations to describe how this happened, and which then had to be verified. In 1918, Karl Schwarzschild solved those equations for the first time, and that predicted how big a black hole would be, how big the objects that Laplace had proposed would actually be according to Einstein's theory of general relativity. So, and that, you know, now Karl Schwarzschild was unfortunately killed at the very end of the First World War, so he couldn't continue his work. But his name is famous throughout the black hole area as the description of how big the emitting region is. So broadly, two kinds of black holes. On the left-hand side, we've got stellar black holes, which are caused when massive stars collapse. And they were first generally accepted to exist in the late 60s, early 70s. An object called Cygnus X1 was discovered, which had a massive star of 20 solar masses and huge amount of X-rays. And also it was going around an orbit of 20% of the size of the Earth's orbit. And so the only real explanation that was possible was that it was this kind of system where the 20 solar mass star had a companion that had collapsed silently, as it turned out. There's no evidence that there was a supernova explosion. Sorry, Malhar. But this is emitting copious X-rays. But we're not talking any more about that, because the interesting ones are the ones in the centers of galaxies. And it's now thought that nearly every galaxy does have a central black hole. And how does that happen? Well, the same kind of accretion disk, except that stars are sucked into it and it simply grows and grows. The centers of galaxies are very dense, and as a result, you end up with a monster black hole, which is several million solar masses or even billions. If we look in the center of our own galaxy, we actually can see, if this comes up, stars moving really fast. This is time-lapse photography, but we can actually detect the motion of the stars around the central object in our galaxy, and the fastest ones are whizzing around the location of the central black hole at 10% of the speed of light. Imagine that. We have been able to send around our sun. Oops.
What do you think comes next?
I'm going to go 7.
7.
Excuse me.
Actually, it's another 3. Now you have a guess what's coming next.
Excuse me a second, guys.
Yes, as a matter of fact, it continues to be 3, 3, 3. And you wonder, this is really a strange sequence, you know. What are we going to do with this? Well, This is the number.
Sorry, that's the problems of using YouTube. Okay, so what would a black hole look like up close? Well, there's a great video that I don't have time to show you that explains why the shape of why a black hole would appear to be the shape that it is. But on the left, when you simulate that, you get something that looks like this. And on the right, this is what is actually observed. With the resolution that it has, it's right in the middle of the large Virgo galaxy M87. I have a couple of words about M87. For years, it's been known as the largest, but not one of the largest galaxies in the Virgo cluster. It's 53 million light years away. And if you look very carefully at this picture, you see there's a jet that is coming out of the center. That jet was also discovered in 1918. And it's taken until now to figure out what it is that is causing the jet. The Event Horizon Telescope collaboration looked at the jet, has been looking at the jet. If you look to look for the central black hole, of course, by the name, you can tell it's really looking for black holes. The Event Horizon Telescope is a collaboration, massive international collaboration of many, many observatories around the world. I don't know whether I care to hit this link and get the wrong YouTube video playing again, but eventhorizontelescope.org will tell you all the details. One of the principal telescopes is the ALMA Atacama Large Millimeter Array, which is partly a Canadian project. It has 67 dishes that can resolve incredibly small objects in a long distance away. The black hole itself, which you saw briefly earlier, and I'll show you again in a minute, is 42 micro arc seconds across. And if you look at what that means in terms of scale, the diagram on the left, here's the jet that we've known about since 1918. It's this long. This is from pure ALMA observations. So that's what the radio telescope it can do without all these other telescopes around the world. And then the very large baseline array can look into that central ball where the center of the galaxy is and sees this. And then the Event Horizon Telescope collaboration can see the middle, and that's 6/6,000ths of a light year across is what we're talking about. That's very small because their radius is determined by the Schwarzschild radius, which we heard about in the middle. And if you actually do the math of understanding how black holes warp light, it turns out that this shadow here in the middle is 2.6 times the Schwarzschild radius. And that's because of the way that light is bent around the center. So we saw this picture roughly at 2019. What is new this week is if you see these lines on this picture, and those lines have been discovered to represent the magnetic fields involved. So we know, and this was done by the EHT collaboration. If you look further at this, you see that ALMA puts in ALMA by itself can't resolve this picture, but the whole collaboration does. You've got all of these lines that represent magnetic fields, and through polarized observations, we can see that this disk, which is around the black hole, is very magnetic. The bright point at the bottom it's the size of this. So it's of order several times the size of a solar system, not bigger. The work is just spectacular. And that's my brief history of black holes. Thank you.
Thanks, Ben. To add in a little bit there, I took a look at one of the papers about this particular research, and I found something that I just love because it just shows how silly physicists can be. And it has to do with the modeling that they did to understand the polarization of the light that they got from this black hole. Basically, they did a measurement there directly. They had to model what this black hole environment looked like, what types of magnetic fields might be around it. And then sort of from the see which of these models best matches our observations. And depending on the strength of the magnetic field around the black hole, simulations fall into one of two categories. If the magnetic field is really strong, you get something called the magnetically arrested disk, or MAD state. And if the magnetic field is fairly weak, you get instead the standard and normal evolution, or sane state. So these black holes can be either mad or sane. So if anyone gets too far into black hole physics, I think the mad part tends to be more common. All right, and now I'm going to show you all a little bit about the, oh, can't hear me. I apologize, my headphones have been giving me some bad.
Helicopter with a essentially piggybacking on it. But once they're down on the Martian surface, how do we make sure it down upside down, or that we don't accidentally knock it with the and where do we fit this thing so that it doesn't get in the way of the rover as the rover itself is trying to land on Mars? And so what they've come up with is crazy. They essentially took the helicopter, lined up the blades, packed in the legs, and folded it up in this little rectangular package that sits on the bottom of the Perseverance rover. And then once it's on Mars and it's found a good spot, it has to very, very carefully gravity. Then the rover backs away and it'll sit there for the next several days or a couple weeks, actually. Ingenuity helicopter goes through all its pre-flight checks, sure everything's going right, and then finally tries a couple of actual flights on another world. And I think that's all I have for you right now. If we have some time at the end, I'll come back with some more information on the Perseverance rover. Let's see, stop share there. And finally, and next up, let's see, we've got our main speaker, who I'm going to turn over to Ben to introduce. Oh no, sorry, do we have, let's see, do we have Brock Johnson on?
Yes, I just joined.
Excellent. We were going to hear from you about the supernova image you just took.
Okay. Let me share that then.
Fantastic.
Okay. Might be a bit of a, I have to get it too. So I am sharing this one. I don't know if I go into full screen mode, whether it'll work. I'm not sure. No, no, it's on the other screen. Hold on.
If you try going to full screen and then start the screen share, you may be able to select the full screen version.
I think so. There we go. So, can you guys see this?
Yes, we can.
Okay, so yeah, anyways, it was, there was some, David had sent around a couple of things talking about this new supernova, and it was near in Cassiopeia, and not far from the Bubble Nebula, according to Sky and Telescope. And there were a few articles, and there's another shot here. And thankfully, they gave some coordinates, and which was really, really helpful. And so David mentioned that it'd be good to go and see it, and I got out my telescope, and I can't claim a lot of credit or skill here because I have some pretty cool hardware which made it really easy. But basically what I was looking for was this nova here. And one of the things I like to do before I dive into something like this is try to get a sort of an image in my head of the stars in the local area, just so that I can recognize them once I actually get a preview in my telescope. So this is the picture zoomed in, the one from this Astronomy Now magazine. And you can see that there's this little triplet of stars, and there's 2 bright stars, and there's this little cluster here that's kind of recognizable. So I kind of got my head around what that looked like. And then I set up my telescope in the backyard. It's a Edge HD from Celestron. And the thing that really facilitated me finding anything at all is probably this great little ASI which is a little Raspberry Pi based mini computer.
Have we lost him?
I think we may have lost him.
Oh
He looks like he's frozen.
Yeah. Okay. Well, we may have to bring him back after the speaker.
Sure.
Hopefully, he gets his internet setup figured out. All right. So let's move along then to our main speaker. I will let Ben introduce him in just a moment, but for those of you on YouTube at the moment, it sounds like we've been having, thank you. For those of us on YouTube at the moment, it sounds like we've been having some technical difficulties there. I would like to apologize for that. This is our second time trying to stream on YouTube as well, and we're still working out some kinks. We've posted
apologies from me.
We've posted the Zoom link in the chat of the YouTube video. If you'd like to join us over on our Zoom call, where we seem to be having fewer technical difficulties. So hopefully you're able to join us there for our main speaker.
Relatively
Ben,
fewer.
take it away.
Yes. So I'm very pleased to introduce Malhar. We connected through the fact that our wives work together, as it so happens. But then when I started looking into what this guy has actually accomplished, I thought this is amazing. We just have to have him to talk to this group of parents and amateur astronomers. Malhar is a director of the Prince George Observatory. He has been, you're still a graduate student, right?
Yes, I am.
Right. So that's pretty amazing in itself. He has forged an international collaboration called the Global Supernova Search Team, which is the subject of tonight's talk, with collaborators across the pond. And he's also had a lot of presentations with locally, so he spends his copious free time educating at libraries and schools, and as well, he follows his passion to discover supernovae very successfully. He's been on CBC to tell the world the rest of the story, and we're very much looking forward to hearing it. So with that, I will stop talking and give you the stage.
Hello, thank you so much, Ben, for the introduction. So hello all, I'm Malhar, and I am really excited to join you all this evening in the virtual star party of Dominion Astrophysical Observatory. And in tonight's presentation, I am going to talk about Global Supernova Search Team, which is also called GSNST. And in 1 second, I'll share my screen. Okay, can you guys see the screen? Okay.
Yes, we can.
All right, awesome, thank you. So I'm a principal investigator of Global Supernova Search Team, and recently I got actually elected as a president of Prince George Astronomical Society, RASC. And in the overview, I'm going to talk about what Global Supernova Search Team is. So our team, which is the first sky survey in Canada dedicated to search for astronomical transients. And we founded this team in 2018 with 2 astronomers from Canada and France. And in 2018, we scanned some Northern Hemisphere sky and discovered 3 supernovas in 2018. Also, GSNST grew in capacity of 3, totaling 5 members, including astronomers from United States, India, and Argentina. In 2020, GSNST became, we are officially all sky survey, covering both Northern Hemisphere and Southern Hemisphere now. And in 2021, this year, we have 10 astronomers from all over the world, from Canada, France, India, United States, and Argentina. And why do we survey the sky using different telescopes located all around the planet? The main goal for GSNST is to search for astronomical transients such as novae, supernova, optical counterparts of gamma ray burst, and also optical counterparts of gravitational wave. I am actually thinking to collaborating with LIGO Virgo this year. And also to know about the intrinsic and extrinsic details of any astronomical object. And also, in contrast to studying a single object in space, the survey meaning like we usually don't point our telescope at one part of the sky. We usually survey entire sky every possible clear night, and we scan over 200 galaxies every single night. And the importance of finding some rare supernovas, deepens our understanding of formation and expansion of the universe. So how GSNST survey the sky? From Prince George, we have a wide field survey camera, which is mounted on our 0.61 meter telescope at Prince George Observatory. And we try to observe northern sky twice, every cadence of 2 days in north, if weather permitting. And using Prince George Observatory, we have discovered 17 supernovas and 3 novaes in Andromeda Galaxy. And the limiting magnitude for 24-inch telescope in Prince George is 21 magnitude in 60-second exposure. We are also trying to get ultra-wide field camera so we can take pretty pictures of the night sky and create a map, and hoping to hold the map, it will be online for public and all the data will be available for public. And other main telescopes we have is one in northern Spain, which is a 8-inch refractor, and one in southwest France, which is a 12-inch reflector telescope. We also sometimes use SLU observatories for confirmation of some of our discovery if the skies are not clear in any of the region where our telescopes are located. And another telescope we have, it's in Arizona Sky Village, which is a 0.5 meter telescope. And the 6th telescope we have is in OSOUS, which is also half-meter telescope. Another one is in Mont Megantic in Quebec, one in Benson, Arizona, and another one in Frontenac, Quebec. And these are the location of all the GSNST observatories. So, and I created the all sky survey map of the GSNST, the sky covering. So we are covering all north and southern hemisphere every night, depending on weather.
Malhar,
Yes.
I have a question from the chat. Someone's asking you to explain limiting magnitude.
Okay, so limiting magnitude is, for example, if I'm observing with, in 60 seconds, what is the highest magnitude you can reach with your telescope and your CCD camera? So in 60-second exposure, our Prince George Observatory, which is a 24-inch telescope, we can reach 21 magnitude if the sky, depending on the sky condition, photometric sky conditions. So if the sky conditions are really good, we can say maybe 0.8 arc seconds, then we can definitely reach 21 magnitude.
Okay, and for anyone who's not familiar with magnitudes, the magnitude system sort of works a bit backwards. The higher the number, the dimmer the object. So
Yes.
limiting magnitude works sort of like it's the dimmest object you can see based on your observing conditions. Is that right?
Yes, that's absolutely right. Yes. So when we go high, it means like plus 20 or plus 19 magnitude, meaning the object is really faint.
Okay, thank you.
Thank you so much. And the sky coverage we call it is meaning the sky, the GSNST, all the telescope we cover every 2 nights. Okay, so since 2018, we have monitored over 14,000 galaxies in northern and southern hemisphere. And until today, we have 137 discoveries to date. Also, we continuously scan both hemisphere in the cadence of 2 days, meaning we scan entire sky every 2 days. So if there is a new supernova, or if there is a nova or a flare, optical flare from a star, we try to capture that really quickly depending on weather. Also, we are surveying the north and south every possible clear night down to magnitude, very, very high magnitude, from 19 magnitude to 22 magnitudes. Most sky surveys these days, they're observing for 50-second exposure for the galaxies. But we are actually trying to observe each target, meaning each galaxies for approximately 300 seconds, which gives us to go down to 22 magnitude, meaning really faint targets, really faint objects in the universe. And here's our discovery map of how many supernovas we have discovered and what part of the region. So I am still have to add a lot more discoveries in these. This is actually from one of our paper we are writing it right now. So you can see here we are covering almost entire sky. Okay, and all these red triangles, they are plus 19 and plus 18 magnitude discoveries. Early science results from GSNST. So this was one of our discovery we did last year in NGC 5157, and this supernova got classified as type 1A supernova. And some more, added some more pictures from our discovery last year. This is type 1A discovery again in an unknown galaxy. And GSNST 20CO was a type 2 supernova, also in an unknown galaxy. And we also discovered an optical flare of the quasar in 2020, last year. also, by monitoring all the entire sky every possible clear night, we are creating a map of variable stars. So this data will be available for public who can discover their own variable stars, and they can study the O-C curve and the radial velocities of the variable stars. And GSC 0762-2924 was one of my first discoveries of a delta Scuti variable type star. So we will, move on to what are supernovas. So supernova is an event that occurs upon the death of a certain type of stars. And why do we study supernovas? Why do we survey the sky every possible clear night, and why supernovas? Because they are actually one of the most important objects in our universe to study. And a supernova burns only for a short period of time, right? And yet supernova can give us a lot of information about our universe. For example, to learn more about the acceleration of the expansion of the universe. And GSNST, we are all trying to discover high redshift supernovas, meaning the supernovas are really far away. And so we are trying to discover those. Some of the discoveries we did last year, they were low redshift supernova. For example, the supernova in NGC 5157, this was a low Z supernova. So it was close by, nearby galaxy. And when we are searching for supernovas, we compare our archival data. So we are also creating a map of all the galaxies, all the faint galaxies, which we scan using our different telescopes. And then when we have archival data, we compare our old data to our new data. And then we see if there is a new supernova happened in the galaxy. By scanning or 100 or 200 galaxies every possible clear night, we are hoping to discover at least 1 or 2 supernovas every night. And the word supernova was actually coined by Walter Bade and Fritz Zwicky. So here's Fritz Zwicky and his 18-inch telescope at Palomar observatories. And now this is a Zwicky Transient Facility. This is ZTF is right now is actually one of the most leading sky surveys for supernova searches. So ZTF is actually searching over 50 to 70 supernovas every clear night, down to magnitude 20. So they're also discovering very faint supernovas. But the difference between ZTF and GSNST, it's ZTF it's all automated. There is no human involvement in searching supernovas. But in case of GSNST, we are actually doing everything manually, except our robotic telescopes. So we actually search supernovas by eyeballing method. So we actually compare image using, look at the computer screens and try to find the transients. So in Latin, nova means new, referring astronomically to what appears to be temporary new object in the night sky. Okay, and when we add a prefix super in that word, so it distinguishes supernova from ordinary nova, which are far less luminous. Okay, so novas are actually far less luminous from supernovas. Okay, and here is a picture of one of the supernova we were studying using our Prince George Astronomical Observatory in 2017. So this supernova was in NGC 6946. And we studied this supernova for 7 months. And by doing some science and photometric, meaning the measuring the magnitude of the supernova and how the magnitude is decreasing. So we calculated the magnitude was decreasing 0.001 0.02 per day magnitude. So it was decreasing. And then after 9.5 months, the supernova disappeared. So we had 100% completeness of this supernova. But right now, for GSNST, we have 5% completeness rate of the supernova, meaning we are trying to study the supernovas from the day it actually explodes to the end of the supernova, like when the supernova disappears. So we are trying to increase our completeness, but because of the survey, we can't do that. But we are still trying really hard to get more time on telescopes. And so supernova happens where there is a change in the core of the star. Okay, and the change can occur in two different types, right? And with both resulting into a supernova. So
Malhar.
Yes.
Hey, just to quickly go back to one thing you mentioned before, just another question. So you mentioned that you were looking at these, looking for these supernovae manually. So Lori asks, are you using something like the blink method, where you swap between two pictures to see what changes?
Well, I sometimes use the blinking, but most of the time I use a software DS9, and I keep one picture on the right hand side and one picture on the left hand side, and I just compare two pictures using my eyeballs.
Oh wow.
Yes.
Okay.
Thank you.
Yeah, thanks.
So the first type of supernova is type 1A. And the type 1A actually happens in a binary star system, meaning there are two stars. Okay, so the binary stars, the binary stars are the two stars that are orbiting one another, okay, in which one of the star is a white dwarf. And in this picture, we can see on the left, we can see there is a white dwarf star, and the red star is a red giant star. Okay, the other star, which is orbiting a white dwarf, could be from anything from a giant star to even a smaller white dwarf star. And eventually the white dwarf star accumulates so much of the matter from its companion star, from the second star, and the star explodes in a supernova. So that is a type 1A supernova. And in the sky, we can actually see the remnants of type 1A supernova. For example, M57, or we call it Ring Nebula. And so what are really white dwarf stars? So white dwarf is an extremely dense star, and its mass is comparable to that of the sun. Okay, and the volume of the star is comparable to that of the Earth. So in this picture, we can see the white dwarf star is really small as compared to the sun, but the white dwarf star the mass is almost as the sun, and the size is almost close to the size of our Earth. And here's a type 1A supernova in UGC 9544. This is not my discovery. This supernova was discovered by Lake Observatory in 2018. So we were monitoring this supernova for a month. And another type of supernova is type 2, which occurs at the end of a single star's lifetime. And what happens in type 2 supernova, when the nuclear fuel, some of its mass flows inside the core of the star, inside the nucleus of the star, and eventually the core actually gets too heavy, okay, and it cannot withstand its own gravitational force. And that type 2 supernova is also called core collapse supernova, because all the matter, in this slide, you can see all the fuel actually runs in the core of the star. Okay, but for type 2 supernova, the star must be at least 40 to 50 times the mass of our sun. So the star should be really big. Okay, and for comparison, here we can see the sun is on the left corner, and it's just a small, dot in the screen as compared to Antares, which is a very, very big star. Do we have any questions?
Yeah, we've got one more question. What's the field of view of your the Prince George telescope?
Oh, it's 16 by 16 arc minute. 16 by 16 arc minutes.
That's all the questions I see currently.
Okay, thank you.
Mm-hmm.
And here I have added a animation of Type 2 supernova in Large Magellanic Cloud, which is SN 1987A in LMC. So we can see in the core, the star is actually going into a supernova, and we can see all the shock waves. Last year, actually, I was monitoring SN 1987A and trying to capture the light echoes from the supernova. And I'm still actually working on that. I'm still processing that data because it's a large amount of data.
Can you describe what a light echo is?
The light echo is actually when a supernova happens, we can say them as a shock waves. Shock waves going far away, and we can capture those shock waves by taking long exposures, for example, for days and days. And there is actually an astronomer from an amateur astronomer who captured those light waves from New Zealand. And that's when I got an idea to try it out. And I've been trying that out I actually took pictures for at least 15 days for 2 hours. I took some time from the survey, and I still have to process that data. But hopefully it will be, I should be able to see those light echoes.
So in this case, are you looking for the gas that's expanding from this supernova that's ramming into the interstellar medium?
Yes.
Or are you looking for, okay, so not the flash that's like bouncing off another cloud of gas?
No. I'm looking for the remnants.
Okay, gotcha.
Thank you.
And we have one more question from Ben.
Yes.
Who are your collaborators in other countries, and how did you get in touch with them? Although if you want to save that one for the end of the talk.
I can say that at the end of the talk, if you don't mind, Ben. Yes.
Sounds good.
Perfect. Thank you so much.
No problem.
So, and then novas. We have discovered a couple novas in Andromeda Galaxy, and also one variable star in LMC, Large Magellanic Cloud, last year. So I think in total, last year, I discovered 4 novas and 1 variable star, and in 94 supernovas. So in those 94 supernovas, there are some, gamma ray burst, and some of the active galactic nuclei, the galaxies which are really active in the center. And so we discovered that. And some of the supernovas got classified as type 1A and type 2. And then we'll come to novas. So nova is actually an astronomical transient event that causes the sudden appearance of a bright new star. Okay, that slowly fades over several weeks or many months. For example, we have a nova in Cassiopeia. Right, and I actually took a picture of that nova a couple of days ago. So there's my picture of V1405 Cass. I still have to pictures of this nova, and maybe tomorrow night it's going to be clear, and I'll try to actually get some more information about this nova in from tomorrow. I haven't done the photometry for this nova, so I don't really know what is the brightness of this nova right now. But And we, so there's a reporting system when we report all our discoveries from GSNST. When we discover a supernova, we don't just report it right away. We follow a process. Okay, so the process follow-up observations. So if I find a transient, if I find a supernova in one of the galaxy, then I will send an email to all my colleagues, and we'll try to get follow-up observations of that supernova. Okay, if it's a real false positive, meaning if it's a false positive, then the object won't show up in our CCD chip. When it shows up on our different cameras, different telescope at the same position, then we report our supernova discoveries to transient name server. Okay, so the reports, amateur astronomers can report the discoveries here, and most sky surveys, we have automation, automatic discovery reports. And there are brokers, for example, Pan-STARRS telescope. And on the other hand, we have different alerts. So on the email, we get alerts from different transients. We also get alerts for classification of supernovas and fast radio burst and gravitational events, and also astronautes. So astronautes are if there is a really interesting transient, for example, 2018 cow, COW. So we get alerts from astronauts as well. And TNS is an official transient reporting mechanism, okay, from IAU, International Astronomical Union. And it is all the data is publicly available, so anyone can create an account on TNS, and they can have access to all the data of all the supernovas which surveys have reported, all the sky surveys. So right now we have 13 professional sky surveys which are searching for supernovas, and one of them is GSNST. And this year, right now, we are on number 5th in the world to search for supernovas. First is CDF, then Atlas, Pan-STARRS, Gaia, and then GSNST.
Wow. So I have a quick question.
Yes.
So when you discover a supernova, so you do this follow-up process, how fast do you have to do it in order for other follow-up observations from other observatories to get a crack at it? I know supernova are very interesting for their spectra. I don't know if you take spectra or if you report that and then other people will try and catch it.
We do take spectrum sometimes. If the supernovas, depending on the magnitude, that how bright the supernovas are. Okay, and sometimes if we discover supernovas in southern hemisphere, then there is a telescope called NTT, New Technology Telescope, which is a 4.5-meter telescope, and they have a supernova classification program, okay, called ePesto. So sometimes they classify our discoveries. For example, one of the discovery we did in 2019, so it was a tidal disruption event. So they classified that, and that discovery we made, it was with ASASSN, All Sky Automated Survey for Supernovas. And they classified that, and then some of my discoveries, some of our GSNST discoveries, ePesto classified it too. But after for the follow-ups, because right now robotic telescope rules the sky, right? Because there are so many robotic telescopes, and so if we discover a supernova, and we have to be really quick for follow-ups. Okay, in maybe 2 hours, we have to get the follow-ups of the new discovery and report the discovery. So we have to be really fast for follow-ups. Okay, and if the transient is real, and if we couldn't get the follow-up, some other sky survey or some other telescope will actually scoop the discovery. And
Right.
it has happened several times with GSNST.
Oh no.
Yes, actually, two nights ago, there was one supernova reported by an amateur astronomer in, I think, NGC, some nearby galaxy, very bright galaxy, and the supernova was 13 or 15 magnitude. So we actually imaged that supernova 2 nights ago, and the exposure was too high, and we couldn't.
Oh no.
Yep. So we lost that discovery.
It just washed out.
Yeah, it did.
Oh no.
But yeah, that's okay. And the main thing is important to study all the supernovas, even if we couldn't report any discoveries. That's. But the
You can still
important thing is-
contribute to their light curves and all of that.
Yeah, and we do that all the time. For example, with the Gaia, we do that. We do it for ZTF and Atlas and Gaia as well. We actually are hoping to collaborate with Gaia on microlensing events.
Oh, fantastic.
Yeah. So, any more questions? Sorry.
Those are all the questions for right now. Thank you. That was my question. I wanted to jump in.
Okay, thanks. So on this slide, I have added the discoveries rate of GSNST from 2018 to 2020. So in 2018, I actually had no idea how to survey the sky and what galaxies to monitor and how to report the discoveries. So, but I learned and I was reading about sky surveys, and eventually we found 3 supernovas in 2018, and in 2019 I was collaborating. Well, I was doing international projects with Caltech, Ohio State University, and LIGO for optical counterparts of gravitational waves. So we discovered 10 supernovas in 2019, but in 2020 we scanned a lot of galaxies and observed 295 days in a year and found 94 supernovas. So the red one is false positive. So there were 134 false positive and 94 discoveries. The false positive, we don't report false positive ever. And false positive. So if, sometimes I think, okay, there is a possible transient. So I sent an email to all my collaborators and they try to observe it. And those supernovas, those possible iffy candidates, I call them, we call them. So iffy candidates mean they're iffy, maybe they're real and maybe they're not. So we had 134 iffy false positive and 1994 confirmed discoveries. Out of 94, there were some AGN, active galactic nuclei, and gamma ray burst, optical counterparts of gamma ray burst. We also get triggers from Fermi telescope and Swift telescope for gamma ray burst. And the GSNST today, so we are trying to develop an automated transient search pipeline. So there will be no human involvement in searching supernovas soon. And for this year, from January to March, we have 32 supernova discoveries. And for target for 2021 is discovering 200 supernovas in 1 year. Also, GSNST is officially an all-sky survey. We are hoping to increase our cadence by 1 or 2 days at least. And also GSNST is looking for opportunity to set up six robotic telescope in northern BC. For we are looking for grant opportunities to build 6 robotic telescope in northern BC to advance the Supernova Search program. And this is a diagram that how those robotic telescope future plans of GSNST. And those 6 robotic telescope will monitor the entire northern sky every possible clear night. And out of 6, 1 telescope will be for rapid follow-up observations from, to search for optical counterparts of gamma ray burst and gravitational waves, and some rapid follow-ups observations from LSST telescope. In summary, I have the GSNST continues to progressively survey the sky in both northern and southern hemisphere, hoping to discover a rare supernovas. And by discovering new type of supernova might give us more information that we don't know yet about the universe. Also, we will be making all our data available for, publicly available from both hemisphere. So people can use that data to search for new variable stars, and they can use all the galaxy pictures and try to do the photometry in CV band, meaning clear filters, and study of variable stars, times of minima, meaning the calculating the period of the variable stars, and radial velocities of the stars. And these are references. So thank you.
All right, thanks so much for your talk, Malhar. That was fascinating. I've asked for questions from the audience. I have one or two myself, but let's revisit Ben's question. He wanted to know who your collaborators are in other countries and how you got in touch with them to start.
Okay, so for Ben, the first person I saw his post about confirming. His name is Cedric. So he's the co-founder, co-principal investigator of GSNST. He was confirming discoveries of other supernovas in this, from ASASSN and ZTF. And then I actually contacted him about one of the discovery, which was actually unconfirmed. And then we started talking, and I asked him, would you like to, search supernovas? So he was like, sure. So I decided to let's, try to find a supernova group, and we decided to form a new supernova group, which we named GSNST. And in 2019, the project which I was working on a couple of years ago, 3-4 years ago, on Comet 67P. So I had some colleagues which were interested in searching for supernovas. So I asked them from United States and Argentina. So they agreed to join the group. In 2019, then one of my good friend from India, he's a student. So he wanted to, learn. And then he joined the group in 2019. And in 2020, I got more people from United States, from Canada as well. And in 2021, actually, we have 6 people from Canada who are a part of GSNST, 2 people from United States. And well, most people in 2020 who joined the group, they actually emailed me after watching the interview on the TV, which, and the CBC. So they contacted me and they wanted to join the group. So, yeah.
Very cool, thank you. Yeah, true worldwide collaboration. So I guess a lot of the folks who have joined you have set up their different telescopes around the world as well?
Yes, they have their own personal observatories.
Fantastic.
Yeah.
Malhar, I've got a question for you.
Yes.
Your telescope is not very big. In comparison to other telescopes around that are doing some of these all sky surveys, it's fairly small. But is that a problem or a limitation, or is it Is there something else that's more limiting than the size of the telescope?
Well, when I used to work for ASASSN, All Sky Automated Survey for Supernovas, they are using 400 millimeter Nikon f2 Nikon lenses to search for transients. And the telescopes we are using, they're from 12-inch to 24-inch. And other sky surveys, for example, Atlas, they're using a 24-inch telescope too, and they have been finding supernovas which are 19 to 20 magnitude transient. So we are just taking longer exposures for searches, for our search. And all the other sky surveys, they're taking short exposure because they have better CCD cameras. But by taking longer exposures, we can, try to see like higher magnitude, like faint objects. So that's the only difference.
Okay, thanks.
All right. I have one more question as well. You mentioned a tidal disruption event that you caught in collaboration with ASASSN. Can you describe what that actually is?
Yes, so a black hole is actually eating a star, and the star is actually going through a tidal force. The star is experiencing a tidal force. So we caught that, and it was actually one of the brightest tidal disruption event ever observed.
Wow.
And yeah, and we wrote a paper on that, and we are actually hoping to find more of the TDEs, but they're actually very rare to find.
I imagine, yeah. Was this one disruption around the core of a galaxy, or was it a smaller black hole?
It was in the center of the galaxy, so the black hole, the supermassive black hole in the center of the galaxy.
Okay.
And the supermassive black hole was eating the star.
Right.
And we captured that. So it was actually captured by TESS, the Transiting Exoplanet satellite, NASA, and
Right.
then ASASSN telescope. When we were analyzing the data, we saw that, and then we reported that right away. So the star was actually, dying.
Wow.
Because of the black hole.
Fantastic. Thank you.
Thank you.
Let's see. I don't think we have any further questions in the chat. I'll remind folks that we've posted the link again to our poll to ask how you found out about this presentation. We'd love it if you'd fill it out. It really helps us out. Thank you once again, Malhar. We've really enjoyed your talk today. And I think we have one last thing before we sign off for the night. We're going to try and go back to, let's see, I think we're going back to Brock. I think he's joined us again. There he is.
Yeah, I'm here.
To show his supernova image that he got as well.
Yeah, no, I kind of got cut off by, I think sharing a 4K monitor on Zoom wasn't a good idea.
That might do it, yeah.
I got a blue screen of death, so.
Oh no.
Yeah, whole system shut down, I had to restart.
Okay, well, glad you're back with us.
Okay, I'll restart here.
Yes, we got to the, are you talking about your telescope pointing system?
Okay, is it showing again?
It is, yeah.
Yeah, so basically, I guess one thing I left out is these articles, of course, gave coordinates, right ascension and declination for where the nova was. So that allowed me to, I mentioned that getting my head around the star field there and using my hardware. So the ASI Air is a nice little device. This is essentially the screen that I get on my phone. So I was able to enter the coordinates into the ASI Air directly. And so it basically did some slewing and took me to a preview screen. It took a shot, and actually in the preview screen, I could actually see, this is actually the two bright stars in that cluster. This was the nova. And then you can see the three other little stars that kind of created that pattern that I recognized. And I realized it wasn't centered, so I then clicked on the screen and centered it. And now you can see those two are in the center. And then I think I set it for 60, 30-second exposures, but I think I quit after about 10 or 20 because I realized I was just taking pictures of stars. And then this is the final image that I got. So you can see that same, it's rotated relative to the two articles, but there's this little triplet and the two bright stars, and this one here being the supernova, or not the supernova, the nova. I don't think it's technically a supernova, but I keep saying that. So, and I also have, I took the article, the image from the article that also had the crosshairs on it, and I can sort of toggle back and forth so that you can see that I've matching up the two star fields there, and confirmation that I'm pretty sure I've got the right star.
Looks like it to me.
Yeah, so it was pretty neat.
Well done.
I'll take a look over the next few weeks a few times and see if it fades, and maybe David Lee and I can figure out a way to measure the actual brightness.
Yeah, it's David here. I took a slightly different approach to Brock. My mount is actually dismounted right now because I'm modifying it. But I just took a camera out this morning with a telephoto lens and just snapped some pictures. And I kind of cheated. If I could just share my screen, I'll show you.
Sure. How do I release here?
Should be up towards the top, green bar with a red button at the end.
Okay. Stop
or Calvin
share.
could force stop. There we go.
There we go.
I think you're still on, Brock.
David, are you able to share
I'm just
screen?
gonna go do that right now.
And you can start your video too, if you want.
Yeah, so what I did was Brock had such success with this. I thought, well, could I do this with just a simple camera? So what I did was I have a really bad view at dusk, and because Cassiopeia is circumpolar, I knew I could get it on the upswing. So I got up really early this morning at 4, I guess it was, and I took my lens and just put it between the two houses. I have a little gap where I could actually kind of see the Cassiopeia region, and I figured I would just shoot at around 200 millimeters, and I was just shooting at like 6.3 with a slightly elevated gain. I was shooting at about ISO 1600. So, okay, that's well and good, but then how do you decipher all the stars? So that's where I engaged in astrometry.net, which is a plate solving service. So I sent the picture, a couple of pictures up. I kept on missing it, but I was really fortunate. One of the frames had it enough that it was right on the edge of the frame, and I could find it. And you can actually see M52 here, not highly resolved because it's only like a 5-second exposure. But here's that string of stars here. And then I could notify, like, because astrometry.net actually told me some of the values of the stars, I was able to sort of annotate them. So eventually I did find them, and you could see it here. You see a little bit of trailing because I'm not doing any tracking. It's just a camera on a tripod. So I think I did okay. So I found it with a little help from plate solving. Yeah, that's all I've got. And so you too can have a snapshot of the nova.
Very cool. Thanks, David.
You're welcome.
Yeah, thank you both. It's
Thanks, plate
exciting to
solving.
know yeah, it's exciting to know we've got so many astronomers or amateur astronomers in Victoria who are doing some really cool stuff. All right, so that brings us to close to the end. Just for our last little bit here, I believe we've got a quiz from Lori oh, actually, no, there was a question. Oh, no, it was answered in the chat. Okay. So we've got a little quiz from Lori.
Hi, everybody. This is just a little kind of fun thing to end off with tonight. So hope you'll just bear with me. We haven't got this as a poll or anything. This is just a quiz that you can put the answers in to the chat. So we'll just kind of see what happens with this. So if I can share my screen, let's see if this will work. And okay, that's good. Let's do and we'll start. Whoops. Beginning. Okay, here we go. All right. So this one, what can a type 2 supernova, and this is what both Malhar kind of talked about too, a little bit, was what can a type 2 supernova turn into? A nebula, a galaxy, a black hole, a galaxy, or an alien? Write it in your...
Right, yeah, let's see those answers in chat. Ooh, make sure you're not direct messaging anyone.
Okay, what do we cover? I can't see the answers, Aaron, so you can let me know.
I'm only seeing one so far. Any other guesses?
I wonder if there's like a
Just open.
comic book alien that was created in a supernova or something.
Oh, now we're getting some responses.
Okay.
I'm seeing sort of a mix of 1s and 2s.
1s and 2s. Malhar, can you help us? What does this type 2 supernova turn into?
We got a 4. Well, didn't they like make Thor's hammer in a black hole or something? Was that a neutron star?
Oh, interesting.
Oh no, that was
right.
it was a supernova or something. I think so. It could be a hammer for an alien that it could turn into.
Right.
But I think most type 2 supernova turn into, number 2, a black hole, or at least some of them can. The question was, what can it turn into? And it can actually turn into a black hole.
Yeah.
So here is my next question.
I think they can turn into 1 as well. You can get a supernova remnant nebula.
I'm coming back here.
The stuff that shoots out of it, right? And the stuff that
it becomes a nebula.
Well, okay, but a black hole first, right?
Both, maybe?
Yeah, you get the black hole at the same time, yeah.
Okay, all right. Here we are. What process would happen if you entered a black hole? Okay. Rigatonification, macaronification, spaghettification, or fusilification? Oh.
Fusilification, interesting. Well, I mean, if you bring the moon with you, it could be macaronification and cheese.
Hadn't thought of that.
I'm seeing a lot of 3s in the chat.
A lot of 3s. I think so. Yes, I think. Aaron, do you want to talk about what happens with spaghettification?
Sure. Oh, I am on video. Yeah, so with spaghettification, it's basically it's due to the tides around a black hole. Just like the tides on Earth sort of squish in around the sides and pull out towards and away from the moon. That's why we get these bulges of water. You would get the same process, but much, much, much stronger around a black hole. So if you were falling in feet first, you would get squished in around your middle and stretched out from head to toe, and eventually turn into a long piece of atomic spaghetti. And this is what a tidal disruption event that Malhar talked about was. Basically, a star gets too close to a black hole and becomes spaghettified. Instead of being a sphere, it's now a long trail of gas that swirls around the black hole.
And not like rigatoni or fusili, right?
No, no,
No. There we go. Okay.
neither of those shapes.
Next question. What is the name of the crater that the Perseverance rover landed in on Mars? So,
Oh, I don't actually know this one.
Tycho, Manicouagan, or Jezero?
I
Name of the crater.
think I know some that it's not. I think Tycho's a crater on the moon, and Manicouagan's a crater on Earth, I believe. And I'm seeing a lot of 4s, a 1, a couple 2s in the chat. What's our answer?
It is number 4, Jezero crater. Yes, absolutely.
Cool.
That's the one that was very much like some of our deltas and deltas on Earth, and they could actually see from space that it may have been a place where there might have been water before. So that was there.
Wow.
What year did the Dominion Astrophysical Observatory, our beloved DAO, see first light? So first light is when the mirror is all set up, the telescope is all set up, and they open it up and take the very first picture. In this case, it was actually a spectrograph that they took rather than an actual photograph with a camera. They took something with the spectrograph. So 1920, 1918, 1916, or 1910.
Okay, I'm seeing a lot of both 1s and 2s there.
1s and 2s. All right. Well, number 3, 1916, is on the floor of the observatory. You can actually see that because Dr. Plaskett had the entire dome and everything all completely ready to go, the telescope all ready to go, and the mirror was late. And so, in fact, it took another 2 years for the mirror to come in. And so it was actually number 2, 1918. And the answer is May the 6th, 1918 was the time of first light of the DAO.
Mm-hmm.
We're just now in just about May of 2021 that we're
So 103 years.
103 years old. Yeah. Well, there we go. Okay, and I think we have one more. Which one of these is not a constellation? So number 1, Taurus the bull. Number 2, Camelopardalis, the giraffe. Number 3, the Pleiades, the seven sisters. I think I spelled that wrong. Right. And number 4, the telescopium, the telescope.
Well, I definitely see my favorite constellation as part of that list.
Yep, mine too.
Oh, interesting. We're getting a mix of 3s and 4s.
3s and 4s. All right. Well, it's actually number 3. If I spelled it correctly, it would be better. The Pleiades is actually an open star cluster. It is not a full-fledged constellation. The telescopium is actually a telescopium. It is in the southern hemisphere. And my favorite one is Camelopardalis, the giraffe.
Yep, named because
that's mine.
That's my favorite one as well. It's named
I
because
didn't know that, Aaron. There you go.
Yeah, it's because when explorers from Europe went to Africa, they came back with this tale of a beast that was like, it looked like a camel. It was with a super long neck, but it had a leopard spots. So they called it a camelopardy.
Yeah.
Before they got the name giraffe.
Yeah.
And then telescopium is part of a whole bunch of southern constellations that are named after more modern things than we see in the northern hemisphere. And this is very Eurocentric. Most of our constellations come from Greek and Roman mythology. They could only see so far down into the southern hemisphere of the sky. It was only when Europeans had big sailing ships and could go sailing down into the southern hemisphere that they started naming these southern constellations. Of course, the Polynesian peoples had names for constellations all over the sky,
Absolutely.
thousands of years ago, but the
Yeah.
ones that are officially recognized and used for sort of mapping out the sky by the IAU do have this little historical like quirk of the eras.
Yeah.
This Don here. Can anybody remember the science fiction series where when somebody got excited, they would exclaim, "Camel Partilus"? I don't remember which one that was. Might have been like Star Galactica or something like that. The original.
Not a clue, sorry.
Nope.
Bit of
We're
trivia
losing it
for next
completely.
time.
That's hilarious. That must be really obscure then, if Aaron doesn't know.
Now, so I'm going to stop sharing my screen because in
All right.
fact it is now 8:37 on my
Mhm.
screen here, and we are officially into something called Earth Hour. So do you want to talk about that a little bit, Aaron, and we can then just sign off, and everybody should be now getting up and turning off all their lights.
All right. So
Yeah.
I'll turn off some of my lights here. Basically, if you haven't heard of it before, Earth Hour is an hour to raise awareness of energy conservation. And everyone's encouraged for the hour between 8:30 and 9:30 this evening to turn off all lights and unnecessary electronic devices for the full hour to get a sense of what would happen if we didn't have electricity helping us power our homes, and what we can do to conserve it as much as possible. And with that, I think we'll be signing off for the evening. Thank you all so much for joining us. If you haven't already, please fill out that poll and let us know how you found out about this today. And we hope you'll join us next month for our next Saturday night star party. Thanks again, and have a great night.
Okay. Bye now.
Bye.
Good night, everybody.
Night.
Night.
And yes, thank you again to Malhar for his excellent talk this evening.
Good night.
Thank you so much, guys, for having me. Thank you so
It was a
much.
pleasure. Thank you.
Good to meet
Thanks
you all.
everybody for joining in.
Have a good night.
Good night.
Good night.